Greetings and welcome back. Today we're going to be going back away from spectroscopy and into functional groups again and their reactions. So as a general reminder, as we did in Organic Chemistry 1, we'll be doing each functional group at a time, first talking a little bit about how we name them and an introduction to them, which we'll be doing in this video. Next we'll talk about how we synthesize them, which will often be a little bit cumulative because a lot of the reactions to make these now are things that we covered last semester. And thirdly, we'll be talking about reactions of them. So, let's start off with a little introduction and how to name ethers. First off, as a brief introduction to ethers, you hopefully remember that ethers are molecules that have an oxygen with two single bonds to a carbon on both sides. If there was a hydrogen on one side, it would just be alcohols. But ethers, on the other hand, have carbons on both sides. Therefore, the main thing about ethers is they're not acidic. They don't have an OH, and certainly the carbons next door are not generally acidic. So they're not acidic, which means that they are good solvents. Reasons for this are that you can use nucleophiles, which are often bases, and those will often pull a hydrogen off of something like an alcohol, or a ketone or something like that. But in this case, there are no hydrogens to be removed, so they can react very safely with both strong nucleophiles and strong electrophiles. Probably the most common ones that are used are diethyl ether, which looks like this. It's just two ethyl groups, one on each side. And also some of the solvents, for instance this one. This is a very similar structure, only it's a ring. This one is called THF, which we'll talk about very briefly where we came up with the name of this one. But this is THF. This one on the left here is called diethyl ether for hopefully understandable reasons. Has ethyl groups on both sides. Sometimes it's just called ethyl ether. And sometimes it's just actually called ether. So if people talk about ether, that's the one they're talking about is diethyl ether. It's by far the most common. So in general, this chapter is relatively brief because there's not a lot of reactions of these ethers, which is part of why they're great solvents. They don't react, and that's what you want from a solvent. You want something that will dissolve things, which these can because they're a little bit polar, a little bit non-polar. Right? They do have these dipoles. However, they don't have any, they can't make hydrogen bonds to themselves or anything like that. So they're good solvents because they're not reactive with anything at all, really. We will talk very briefly about the one notable exception to that, which is really strong acids, but that's about it. Pretty much they're just great solvents. As I mentioned in the last slide, the common names are something, YL, something, YL, ether. And that's generally the way that we name ethers. So for instance, if you had a CH3O and then a propyl group, the quote-unquote common name of this would be methyl propyl ether. And that's the way that these are commonly named. We can also do this with thioethers, which react in very similar ways. A thioether would have a sulfur in place of the oxygen. So sulfur is not something that we often use. However, it is something that has similar reactivity to that of ethers. Therefore, these thioethers pop up in this chapter. So the way that we name a thioether is something on one side, something on the other side, sulfide. So for instance, in this case, we would have diethyl or ethyl-ethyl sulfide. An ethyl group on each side. So this would be diethyl, because there's just two of the same thing, sulfide. Right? And the name of this one above, if you didn't write it down, was methyl propyl ether. So So you can see that for most relatively simple ethers, this nomenclature is absolutely sufficient, and we can use common naming. In fact, it shows up quite often because most ethers are relatively simple. However, we have quite a bit of large molecules that will have multiple functional groups on them, including an ether. So for instance, something like this, put a double bond there. In this molecule, we could definitely say that on one side we have an ethyl group, but we don't have any really good way to name this as a substituent. So of course, when molecules get more complicated, the IUPAC nomenclature is the way to go. So let's draw that again, and I will tell you how we use IUPAC to name these guys quite easily. Alright, so the way that IUPAC works is that ethers, or at least the ether part of the molecule, is never the main chain. The key to this is it is always a substituent. Always a substituent. So the main chain here would be the chain with the alkene on it, and we would just name this group as a substituent. The way that they're named as substituents is alkoxy. And in case of a sulfur, we would name them as alkyl thio. So that's always a substituent. So if we remember our nomenclature, we would start at our alkene. 1, 2, 3, 4, 5. So my main chain here would be a 1-pentene. The 1 indicates the location of the alkene. And then we would have that substituent right here at carbon number 4. These are called alkoxy, so in this case you can see it's 2 carbons, therefore it would be an ethyl group. So instead of saying ethyl, because it's alkoxy, we would say ethoxy. So this would be a 4-ethoxy 1-pentene. And this could be anything. If it was 1 carbon, it would be methoxy, isopropoxy, etc., etc., etc. So let me go ahead and do a sulfur-containing one. Alright, in this case, the main chain would be our cyclohexane ring. And we could number really from whichever side we want, because rings don't have sides. So we assume that this group is at carbon number 1. And this would be, because instead of alkyl thio, in this case specifically, we have 3 carbons, 1, 2, 3. So it would be a propyl thio. So this would be propyl thio cyclohexane. And that is how you name these guys in terms of IUPAC. It's actually quite nice that we never have the choice of making it our main chain. Therefore, these guys are always substituents. The priority is at the bottom. The reason they're really low priority is because priority tells us what is going to be part of the main chain. These will never be part of a main chain, so they are the lowest priority of all functional groups. And that is the priority for naming and numbering. Alright, so I will give you a slightly more complicated example for you to work out, and this will be the first thing we'll go through in class. Let's try to do and I will just go ahead and make it exciting and put a double bond in there. So see if you can name that one, and we'll talk about that first thing in class. Lastly, I want to mention ringed ethers. So we saw one at the very beginning, which was the THF. This guy right there, it probably rings a bell. We saw THF complexed with BH3. BH3 was borane and wasn't very stable, and so sometimes those things were complex together. The oxygen was able to make a very, I guess, transient single bond with that boron, but that's neither here nor there. The point is that this is THF. Where that comes from has to do with this molecule. This molecule, which is very similar, 5-membered ring with 2 double bonds and an oxygen, is technically an ether. It's a ringed ether because it's carbon, oxygen, carbon, C. But instead of just being a straight chain ether, this one is in a circle, just like this one is here. This one on the bottom is called furan. That is the common and the IUPACK name of that molecule. You'll notice that the difference between these two molecules is that the one at the bottom has 4 hydrogens, and the one at the top, in the process of removing those double bonds, now has 4 more hydrogens. It has 8 total hydrogens. So what THF stands for is tetrahydrofuran. Tetra meaning 4, hydro referring to hydrogen because it has 4 extra hydrogens compared to furan. So that's where THF comes from. It's a complicated name based on your knowledge of the fact that this is furan, but these are the 2 most common ethers that you will see with more than just 2 carbons. The most common one with 2 carbons is a functional group that we have seen already, which is this little guy. We've called this before an epoxy group, and it is named an epoxy group, but that's as a substituent. As a main chain, or as a main, if it was the main chain, this little 3-carbon guy, it's called oxirane. So its name is oxirane. So if you saw that guy all by itself, its name would be oxirane. If it was a functional group on a much longer chain, it would be an epoxy group. So there are ways to name these epoxies as well. So let's say that I have something like this. There would be 2 ways that I could name that. Oh dear, everybody wants to move separately. That's unfortunate. Alright, so the 2 ways that I could name that, one would be as an epoxy group, and the way that we would do that would be to look at the longest carbon chain, which would be these 5 carbons right here. We would number it 1, 2, 3, 4, 5. So we would call this a pentane, and the substituent would be an epoxy. So in this case we would have a 2,3 epoxy pentane. And in that process, what we have done is we have taken the epoxy group and essentially said that it is a substituent, just like an alkene or anything like that. The other thing you might notice about this is that it is still a ring, and we have 2 substituents. One is coming out at us right here, and one is going away from us right there. So we can be fairly certain in terms of our, or I should say fairly specific in terms of our nomenclature of orientation. So let's call it trans, because just like with any ring, if you've got one out, one back, it would be a trans molecule. The other way to name this, and I'll draw it again, would be with the oxirane as the main chain, and the substituents just coming off of the oxirane. So let's say this is our main chain. We would want to number these 1. You always start at the oxygen. That's the highest priority functional group within the ring. 2, 3. So we would have an ethyl group coming off of carbon number 2, a methyl group coming off of carbon number 3. The reason I went clockwise from the 1 is because ethyl comes before methyl alphabetically. So this would also be trans, but it would be 2 ethyl, 3 methyl oxirane. Alright, so I'll give you one of these to practice, and then this video will be over. So let's go ahead and I will give you this guy. I'll just put a CH3 there. And on this side, I will have an alkene chain. So see what would make more sense to you and what would be the highest priority in this case. Note that epoxies are never going to be your highest priority functional group because they are just like alkoxies. They're the lowest possible ones. So see if this would be easier to name with the oxirane as the main chain or something else as the main chain, and we'll go through that one first thing in class with the other one from the previous slide. Have a great day, and I'll see you soon.